Hey, in this example, what we're going to do is look at net change for something. In other words, what's the total change that happens, even though it moves all around, how far does a particle actually go, or how much area do we actually cover, or questions of that nature. So what we want to do is we're going to take a look at this velocity equation here, t squared equals, or t squared minus 8 over t plus 1 squared. It gives us this graph shape right here. The initial value on this guy is right here at 0. This is when x is 0. And right there when x is 0, if you put a 0 in for all the t's, you're going to have an initial value of 8. All right. So we would say that our initial value for this, if we're going to describe the motion, we'd say our initial value is -8. That should be a -8 down there. Okay, -8. Or what we would say is 8 seconds, 8, yikes. Let's say that this is, let's give our velocity here some legs, like let's call it centimeters per second. So if we're dealing with velocity, so then what we'd say is we're moving 8 centimeters per second to the left. Okay, 8 centimeters per second to the left. Anything down here is going to be to the left, or away. Depends on what you're trying to interpret. This is usually the guy right here that we're going to use to interpret. It's usually going to be to the left. Okay, somewhere right around in here, we come to a stop. All right, and if we did a little looking, if we plugged this into our calculators and checked it out, we would see that when t is about 1.25 seconds, then we would have a velocity of 0 centimeters per second, because now instead of moving to the left, we're stopping and moving to the right, or instead of moving away, we're stopping and moving toward. Okay, so then if we go above the x-axis, this would be to the right or forward. Think of it as forward. Maybe away is a bad way. Maybe if we said like reverse, that's probably a better way to say that. Okay, so to the right or forward, or to the left or reverse. And all this means is the further we are away from the x-axis, the faster we're moving in that direction. Okay, so we start off at -8 centimeters per second to the left. At 1.25 seconds, we now have 0 centimeters as we're changing from left to right. And then we could finish this by saying, when t is greater than 1.25 seconds, we're moving to the right, and our velocity is increasing. Okay, so we move to the right and velocity increases as we go. How do we know? Because the distance from the x-axis increases, and as that distance gets larger, you're moving quicker. Okay, so we move to the left, we stop, we move to the right, and we go fast, fast, fast. So we're slowing down, stopping, moving to the right, and increasing our speed. So that's the original setup for this problem. We've talked about this a little bit before. We're going to talk about it in a lot more detail in the next lesson. Okay, so let's investigate this particle then from this first position a little bit, from this first example. So we've got this equation, t squared minus 8 over t plus 1 squared, and we go, hey, suppose the initial position of the particle is 9, all right? So what is the particle's position after 1 second and after 5 seconds? Well, remember that when you are working through positioning, we want to know, like, where are we? Like, how much distance have we covered from our initial value of 9, okay? And so after 1 second, what's that going to look like? Remember, when you're trying to find that distance covered, or how far you've moved or changed, you're going to start at an initial position, which in this case is a time of 0, and you're going to stop at a time of 1. So how is that? What does that mean? That means that we integrate our velocity function. If you integrate velocity, you get position. When you integrate velocity, you get position. So we're just going to integrate this guy. T squared minus 8 over t plus 1 squared. And if we want to know where it is after 1 second, then we go from 0 to 1. If we want to know where our particle is after 5 seconds, let me change colors here, then we just go from 0 to 5. Remember, when you integrate velocity, you get position. That's the answer to the question that we're trying to solve. So this would be t squared minus 8 over t plus 1 squared dt. Okay, so those are the problems in that we're going to try and solve. Okay, now keep in mind at the end we're going to have to mess with the 9. Okay, because that's where we started from. So if we integrate these both actually integrate to the same thing because it's the same function. We're just looking at different values that we move across with our particle. So if I integrate this, I'm just going to add 1 to the 2. So I'm going to have 2 cubed over 3. Okay, minus, and then if I'm integrating this, if you just will think for a minute, this is 8 times t plus 1 to the negative 2. And because there's no number in front of that t, when we integrate, we can treat this as its own variable. So this is actually going to be 8 times t to the t plus 1 to the negative 1 divided by negative 1. And that's the same for both of these. Now, if there was a number in front of the t, we would have to use our chain rule and make a u substitution. And the first guy, then we're just going to integrate. We're going to solve it out from 0 to 1. Okay? And when we do that, we end up with 1 over 3 minus, and remember, this is t plus 1 to the negative 1, so it's actually going to be 8 over, and I think this changes to plus because we've got a minus 1 in the denominator. So 8 over 1 plus 1, so 8 over 2. And then when we substitute zeros in, that would be minus, and then 0 cubed divided by 3 is 0, okay? And so that just leaves us the second part here, which is going to be plus 8 over 1, okay? And because we're subtracting that positive 8 over 1, it looks like this. So we put all these bad boys together, and for the 0 to 1 second particle, when you combine all these, I get in my book negative 11 thirds. And I think my math will support that. Okay, so what do? Well, remember, we started at 9. Okay, that was our initial position. So if I start at 9 and I've moved negative 11 thirds, I can put these things together for this guy right here. So I'm going to have 9 minus 11 thirds, which is 27 thirds minus 11, and 27 thirds minus 11 is 16 thirds. So how have I moved? I've moved 16 thirds. Okay, so the initial position, plus this integral down here. And let's name this integral because this is actually a pretty cool thing. We're going to actually call that displacement because this is an idea of how far we've moved. How far have we moved our particle? And anytime you move something, it's called displacement. So when you do initial position plus displacement, you get your new position. It's really a cool thing. So 16 over 3, it's positive. So that would be to the right would be our new displacement if I'm not mistaken. Okay, so 16 over 3 units to the right from our original spot. Okay, that's after 1 second. Kind of cool. Okay, well, let's check out the after 5 seconds thing. So what's going to change down here? Not a whole lot, actually. The only thing that's going to change will be this number 1. Instead of going from 0 to 1, it'll go from 0 to 5. Okay, so this is going to be 5 cubed now over 3 minus 8 over, and actually that would be plus 8 over 6, I think is what it's going to be. 6 squared? No, 8 over 6. Okay? And so when you work that guy out, you're going to end up with 125 over 3 plus 8 over 6. And if I'm not mistaken, that's going to be equal to 35. Okay? So now what I'm going to do, I'm going to take my initial position plus my displacement. So 9 plus 35 should give me my new displacement. So 9 plus 35, my initial position is 9 plus 35. So we'll clear some of this stuff out right here. Actually, we got room right here next to this guy. It'll be 9 plus 35. Wow, I'm getting crowded. Sorry. Which is going to be 44. And again, it'll be units to the right because we're moving in that direction. Okay? It looks really weird, but all it is taking your initial position plus the displacement. What is displacement? Your integral of the function that you're working with. All right, what about total distance over the entire length of the movement for this particle? Well, remember, if I've got velocity, if I integrate velocity, so if I integrate v of t, I get position, and position is usually referred to as s of t, okay? If I know where I start and I add my position to that, I get my total displacement, like how far I moved from where I started. But what if I moved left, then right, then left, then right, and did some kind of weird, herky-jerky, goofy stuff in the process? What if I just wanted to know the total distance I traveled? Like I could move 2 units. If I started, let's say I've got a particle that starts here at 1, and he does all of this, and he stops right here at 2. Okay, let's say this is the setup that I have. Well, if this is the setup that I've got, and I stop here at 2, well, now what? You know, the net change is just 1 unit, but he traveled all this other way. So what we can do is we can actually take the integral, not that one. We can take our integral and we put in our starting and stopping values. So where we start and where we stop, okay? And then what we do is we actually look at the absolute value of the velocity. Now, the one thing you're going to love about this is use your calculator, okay? Because otherwise, integrating absolute value can just be really, really tricky. So what are we going to do? We're going to start here. We're going to stop here. We're going to plug this guy into our calculator. What are we going to plug in? Well, let's look at the second part of that first example where we went through 5 different units. So when I do that, I'm looking at the absolute value now of t squared minus 8 over t plus 1 squared. And I'm taking the absolute value of that with respect to the variable t. Now what? Well, now what means I punch it into my calculator. And when I punch it in to my handy dandy calculator here, you can use the template. You can graph it and graph the absolute value of that and find the integral. We've got lots of different ways to do it. In fact, I'll link in a second video that shows you exactly what you need to do. But when you punch it into your calculator and you do this work, you end up traveling 42.59 total units. Okay, that's how far you've actually gone over the course of the entire movement for this particular particle. So anyway, really, really interesting stuff, and it's kind of fun to mess with, all right? Okay, we've got this car with an initial velocity of 5 miles per hour, and he accelerates at the rate of 2.4 t miles per hour per second for 8 seconds. How fast is the car going when 8 seconds are up? Well, rewind back to what we talked about in the previous couple of examples. If we integrate velocity, we get position. If we integrate acceleration, we get velocity. So to figure out what the velocity is, we're going to take that initial velocity, okay, so I'm going to call it v naught, plus the integral of the acceleration function. It's not hard. We don't, and we may need to know where we start and stop. We might not. It's not going to change a whole lot our problem. It just gives us something to work with, like an initial value. So if I want to know how fast the car is going when 8 seconds are up, I'm going to take that initial velocity v. So my velocity is going to be 5, because that's where I started, plus the integral of 2.4 t dt. And I'm going to evaluate that from 0 to 8. Because I assume we started 0. That's when we have to start our clock. Okay. So what is this going to look like? This is going to look like 5 plus 2.4 t squared divided by 2. And we're going to evaluate that from 0 to 8. And so what would that be when I punch that in? 2.4, that's 1.2, right? So 5 plus 1.2 times 64. 5 plus, let's see, we're going over the 8 seconds, right? So when I punch this in to my handy dandy calculator, I get 81.8, and then this would be miles per hour, because that was the units that we were talking about right there. Okay, and so here we go. And remember too, when you have 0 into your equation, that just makes a 0 for the part that we integrated. So for this part right here is where we're going to evaluate from 0 to 8. Well, if I put 0 in the numerator, 2.4 times 0 is 0, divided by 2 is 0. So it's just going to be 5 plus 2.4 divided by 2 times 8 squared. All right? Not a super complicated deal. Now, the next question, how far did the car travel during those 8 seconds? Well, that now is going to be position. And remember that position is equal to that initial velocity, or our initial position. So let's call it S0, which in this case we weren't given an initial position, plus the integral of the velocity. Remember, if you integrate velocity, you get position. So my velocity, when I integrate this, I've got to figure out, okay, what am I actually working with here? Well, my velocity guy is right here. So I could say that my velocity equation, v of t, is going to be 1.2 t squared. Okay? And so what do I want to do? How far did the car travel during that time? Well, remember, we started off going 5 miles an hour. So whatever we do, we're going to have to add it to that. Okay? Okay, if we want to know how far the car traveled during those 8 seconds, what we have to do is integrate the velocity function. So remember, velocity is this guy right here. Let me get my ink going. Is this guy right here, 5 plus all this, which actually turns out to be 1.2 t squared plus 5. That's my velocity. How do I know? Because I integrated the acceleration, and that's what I got. Okay. And 2.4 divided by 2 is 1.2 t squared plus the 5. We have to have that because we had an initial velocity anyway. Okay, so how can I find my position then? Well, position is just going to be the integral of the velocity, which is going to be 1.2 t squared plus 5t dt, which is going to end up being 1.2 t cubed over 3 plus, and that shouldn't be 5t, that should just be 5. I got all excited here. The t is actually going to be right there. And we're going to evaluate this over those first 8 seconds. So that's going to be evaluated from 0 to 8. You can punch that into your calculator if you want to double check yourself and see what you get. But you should truck along somewhere around 244.8 let's see, miles per hour by seconds. Okay, and why? Because we're looking at 8 seconds for the actual time part. So that's included now when we integrate. So we just have to figure out how to get rid of the miles per hour part and the seconds part. We've got to eliminate those guys. And so to do that, we're going to use our conversion factor. How many seconds in an hour? Okay, how many seconds in an hour? 3,600. All right, so what we're going to do is we're going to take this 244.8 and we're going to multiply it with unit conversion here with 3,600. And the seconds then will cancel out, and that takes care of the hours, and it should just leave us then with just miles. So when you do that, you get a final answer of 0.068. The cool thing, and that's a mile, so we got to have units here. The cool thing with all of this is you can put it into your you can put this into your calculator and get an answer. You can put this into your calculator and get an answer. You can put this into your calculator and get an answer, but keep up with your units. If we're talking about 8 seconds while we're integrating, then we're going to have seconds as part of our solution. So we're going to have to lose those, and that's going to take a little bit of practice to get used to, okay? From 1970 to 1980, the rate of potato consumption in a particular country was determined to be C of T, I guess consumption for C, 2.2 plus 1.1 to the T power, millions of bushels per year. That's a lot of taters. With T being years since the beginning of 1970. Okay, so we're going to start in 1970 and move forward. How many bushels were consumed from the beginning of 1972 to the end of 1973? So think about this for 1 second. We're on a timeline. We're on this timeline, and we're starting in 1970. Okay, and we're going all the way up here to 1980. 1980 is way over here, way up in the future someplace. We're looking at, for us, 1971. Nope. 1972. Yep. 1973. Yep. 1974. Okay. And then 1975. So these are the kind of the years we're looking at. Here's the thing. We're looking at how many bushels were consumed from the beginning of 1972 to the end of 1973. Okay, so if we kind of label these as years, we would have 0, 1, 2, 3, 4, 5. So when we look at this, we're wanting to know how many bushels were consumed. What did we use? How much did we go? How far did we get? And not only how far did we get, how far did we get from here to here? In other words, from years 2 to year 4. Well, we have a way to find that out. Remember, we can find out how far we went by integrating a function over a given interval. And in this case, our interval is going to be years. We're going from year 2 to year 4. We've been given a function, and it's an ugly one. So, hey, guess what? Punch this into your calculator, okay? But set it up. What's the setup going to be? It's going to be from year 2 to year 4, not from year 0 to year 2. That's still the same amount of time, but your graph is changing. And so we've got to look at the specific time period that we're asked to investigate for food consumption. And that period is from year 2 to year 4. What equation do we do? This cool guy right here, 2.2 plus 1.1 TDT. Okay, and punch that into your calculator. Go ahead. It's way easier to do it that way. And what you're going to wind up, and especially with this one, we want to get like a specific decimal answer. You're going to have to use your calculator anyway, because if you integrate from here, you're going to wind up with a natural log running around. So you still have to use your calculator. Might as well just go ahead and use it on the integration part. And when you punch this in, you're going to get 7.06 million bushels. And that's it. That's all we need to know, because that tells us, remember, area under a curve is how far we've gone. Well, if we're consuming at a specific rate, area under the curve would be how much we've consumed. There you go. This is a really handy application of the integration process. Okay, we've got this pump connected to a generator operating at a varying rate. So sometimes it pumps a lot, sometimes not very much. And depending on how much power is being drawn from the generator to operate other machinery. So if everything in the house is running, you don't pump as much, okay? The rate in gallons per minute at which the pump operates is recorded in 5-minute intervals for 1 hour. So how many gallons were pumped during that hour? Now, here's the thing. How many gallons were pumped? This is like our consumption problem. This is the how far we covered problem. This is the area problem. The thing is, we're given time and rate, but we're not given an equation to work with this. We do know this, that if we can integrate this pumping problem, I'll call it P of T, we can figure out how many gallons pumped, okay? And the other thing that we cannot do is we can't go through and just add all the different rates for the gallons, because then you've got to figure out like how much per minute and how many minutes, and it'll just be a really big, ginormous headache, okay? So we've got a couple problems staring at us. The good thing about this is that even though we don't have a specific function in here, we have a way to find the area under this curve, approximate the area very closely. Okay, wait for it. It's the trapezoid rule. It's coming back, okay? Why can I use this rule? I can use the trapezoid rule because I don't have a specific function, but I've got a rate that varies over time, and I've got specific data points that I can use. So what do we need from trapezoid rule? You may remember that the trapezoid rule is equal to h over 2 times y0, that's your first y value, plus 2 times y1, plus 2 times y2, 2y3, all the way up 2 times yn minus 1 plus yn. And the yn minus 1 and the yn are your final terms. Okay? H is equal to b minus a divided by the number of terms that we're using. So what do? Well, our a is going to be 0. Our b is going to be 60. And the number of terms, then, we just need to count up how many times that we're looking at this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So n is 13. So we're going to have 60 minus 0 over 13 times y0. That's the 58 part. And this is going to be really long. And you'll have to write it out. There is no fast way on this, but there is a way. And so you're going to have to write it out so you can keep up with stuff. So this is going to be 58 plus, and then you're going to punch this into your calculator also. 2 times 60 plus 2 times 65 plus 2 times 64 plus, okay, see what I'm going to do? 2 times 58, 2 times 57, times 55, times 55, times 59, all the way up to plus 2 times 60 plus 2 times 63 plus that very last term, 63. Okay, so you add up all these guys. You just punch them into your calculator, pay very close attention to what you're doing. All right. Oh, we forgot to divide all this by 2, by the way. All that divided by 2. That's right there. Right there. Add all that up, multiply it by 60 divided by 13 divided by 2, and that's going to get us about how many gallons. Again, it's an approximation. It's not an exact answer, but I get somewhere around 3,582.5 when I punch it into my calculator, okay? So if you understand what you're doing, you don't have to show me every single step along the way, but you're going to have to punch it into your calculator. What do I need to see if you're in my class? I need to see this setup right here that shows me that you know how to use the trapezoid rule. All right, so how many gallons punched? Well, pumped 358.5 gallons.